Hello, everyone. Well, first of all, I would like to thank the organizers of this conference for making it happen despite all of the circumstances. My name is Mark Akiki. I am a master's student studying aerospace engineering at the University of Illinois, Urbana-Champaign. I work with my advisor, Professor Michael Lembeck, who is an associate professor in the aerospace engineering department. The research I'm about to present is conducted at the Laboratory for Advanced Space Systems at Illinois, and it's about a modular closed-loop test system we started developing about a year and a half ago for the verification and validation of CubeSats. We called this test system the Closed-Loop Analysis of Space Systems class. I'll start off by discussing the problem and research motivation behind developing class. I will also present the specification and design requirements for this test system. I will briefly present the simulation algorithms that are implemented in the class software, demonstrate a full closed-loop test that we performed on one of our 3U CubeSats called CubeSat, and conclude with some future work. So since the establishment of the CubeSat standard over 21 years ago, more than 1,000 CubeSats were launched, and their popularity has been increasing exponentially. To put things into perspective, from 2015 to 2018, the number of CubeSats launched doubled, but the success rate of these CubeSat missions only slightly improved from 56% to 61%. And this is especially apparent in academia, where the failure rate is still significantly high at 55%. According to the literature, CubeSats developers usually identify the cause of mission failure to be associated with either the electrical power system, the onboard computer, or the communication system. But the most concerning statistic is that 33% of CubeSat developers report that they have no means of identifying which satellite subsystem might be the cause of the mission failure. And as you all know, if no communication nor telemetry was established, then doing any form of failure analysis is extremely hard. So this is fairly obvious, but the importance of system testing in improving mission success rate was underlined by several CubeSat developers in government, academia, and industry, according to a survey published by the Aerospace Corporation. These developers were mostly concerned about the lack of time and technology that they have to perform proper verification and validation procedures. Now, while we know that most CubeSat mission failures are unavoidable, I think we can all agree that by improving the verification and validation procedures during the development phase, some of the mission failures can indeed be avoided. So at the Laboratory for Advanced Space Systems at Illinois, we're a team of engineering students that work on the design and development of multiple CubeSat missions. And so to improve our verification and validation procedures and increase our chances of a successful mission, we decided to build CLASS, which is a modular closed-loop test system that is aimed at increasing the reliability of our satellite subsystems. So we set the following requirements for CLASS. The first requirement is that we want it to provide accurate real-time satellite dynamics and orbital mechanics in order to perform hardware-in-the-loop testing. We also want CLASS to be easily customizable by the user so that we can perform different kinds of tests for different kinds of mission objectives and satellite designs. We want to make sure that CLASS relies on widely used hardware, well-documented processors, and programming languages which make it compatible with any type of hardware components or interfaces, especially when testing the satellite subsystem. We also want to mitigate any numerical inaccuracies, especially in the software that is being executed in CLASS. We want to make sure that that software is synchronized with the satellite subsystem being tested. And the fifth requirement we set is that we want to allow the implementation of real-time graphics and visualization during test, which is always a useful tool. So the way we went through and designed CLASS is that we programmed a Raspberry Pi 4 which satisfies the requirement of having widely used processors in the test setup. So we programmed this Raspberry Pi 4 to execute real-time dynamic simulations of a satellite in orbit. This consists of attitude dynamics, orbital mechanics, and space environment models. To have the Raspberry Pi act as an RTOS, we installed a Linux patch called preempt-RT. The dynamic simulation is then interfaced with either the actual sensor or an emulation of the sensor. So for example, you can have a magnetometer sitting inside a Helmholtz cage and have the dynamic simulation command the Helmholtz cage to generate a magnetic field that is expected to be experienced by the satellite in orbit. The magnetometer will then pick up the magnetic field that was generated and send it to the satellite system being tested. Now, as is usually the case with while developing CubeSats, this hardware is not always available. So we have the option of using an emulator for the magnetometer instead of the actual magnetometer. So what this basically is that instead of using the actual sensor, you can use an Arduino board that we programmed to act as the sensor would, by adding sensor noise, by adding any hardware delays, and all different kinds of properties that the user can set. So as a result, the signal that is being received by this emulator will then start to resemble the actual raw data that will come out from a sensor. And then this data is sent to the attitude determination and control system of the satellite being tested. And then you have the freedom of choosing whether you want to test the ADCS on its own or whether you want to have CNDH interfaced with it and so on. We made sure that class is easily customizable for these purposes. And then, of course, to close the loop, the attitude determination and control system sends torque commands. And then these torque commands are received by the attitude dynamic simulation that we have on the Raspberry Pi 4 and applied accordingly. I'll briefly discuss the simulation algorithms that are used in the class software. So for attitude dynamics, we use rigid body dynamics and quaternion kinematics. We use a Runge-Kutta-4 integrator. So here is just one of the many validation procedures that we performed on our software. Over here, I included a satellite that's spinning in a random direction with no torque applied. Then we apply the torque at time equal to 100 minutes, which is positive in the inertial x direction, negative in the inertial y direction, and 0 in the z direction. So the expected behavior here is to have the angular momentum conserved during the first 100 minutes, have it increase in the x direction, then decrease in the y direction, and then stay the same in the z direction, which is exactly what happened in the simulation. And I included more details in the paper of exactly how we made sure that the values we picked up are consistent with the expected values of such a simulation. The orbit propagator we use is the STP4 analytical model, which is a widely used orbit propagator for low Earth orbit. Also, to perform software validation, we ran an orbit simulation for the International Space Station and compared the simulated values we got with the actual ISS values. We had numerical errors of 1.4%, which is acceptable. We also tested the specific angular momentum that was generated in the class software and found it to be consistent with the expected hand-calculated value for the International Space Station during the first 3 orbits of the simulation. The magnetic field model we have in class is the IGRF 13th edition. We also include the environmental disturbances. We have the aerodynamic torque, the gravity gradient torque, and solar radiation pressure is, as of today, included in the class software but has not been fully tested yet. We are currently working on it. So CubeSat is a 3U CubeSat that is being developed at LASI. We decided to use class to test the attitude determination and control system of CubeSat. CubeSat has 3 payloads: a radiator, a quantum annealing experiment, and a fine-pointing attitude control technique. But the control requirements for CubeSats are divided into 2. So first of all, we want to detumble. And then after detumbling, we want to maintain the antenna of the satellite Earth pointing. The way we set up this test, because the CubeSat ADCS flight computer was not ready yet, we programmed an emulation of this flight computer into the class software, which is a good demonstration of the ease of configuration and flexibility we have with such a closed-loop test system. So the ADCS flight computer in CubeSat is not the fastest. So each control cycle takes about 7 seconds to execute, of which 2.4 seconds is allocated to reading sensor data, 2.4 seconds to activate and deactivate all of our actuators, which are magnetorquers, and then we have a bunch of other tasks running in the background. So it was very important to include these hardware delays in our emulation of the flight computer. The first test we performed is the detumbling. We are using the B-dot control law for CubeSat. The initial conditions for this test were set to have really high angular rates of 9.6 degrees per second. The angular rate decreased from 9.6 degrees per second to about 0.065 degrees per second in 117 minutes. As you can see on the graph, which plots the angular velocity versus time, there are many dense oscillations, and these dense oscillations are mainly due to the hardware delays and the delays in the execution of the flight software that I talked about in the previous slides. So here I just wanted to show you what the torque applied looks like for a random control cycle I chose. So it goes in steps because the magnetorquers are not all activated at the same times. They are activated following a certain sequence. And on the right, you can see the magnetic moment that was commanded by the flight software, and it's just simply one step because this is a software command. So had we not included the flight hardware constraints, we would have had a torque applied that is similar to, in shape, to the graphs that are on the right, which is very inaccurate and has a major impact on the dynamics of the simulation. The second phase is to maintain the antenna Earth pointing. The control law we used is similar to a PD control law, which tries to align the satellite body frame with the local vertical, local horizontal body frame of the satellite, which is a very useful coordinate frame that has its z-axis nadir pointing. So this phase starts after detumbling, so we can assume that the angular rates are near zero, but we have reached a random attitude, and in this case it actually corresponded to 113 degrees between the antenna and the nadir vector, which is quite a lot. But in about 142 minutes, so that's less than 2 orbits, the error angle, which is the angle between the nadir vector and the antenna vector, decreased to 0 plus or minus 6 degrees in less than 2 orbits. Also, you can see on the graph that there are these dense oscillations, which are also caused by the hardware constraints I talked about in the slow actuator response. Over here is just a demonstration of the satellite angular velocity settling down at a value that is equal to the circular rate of the satellite, because since we are in low Earth orbit, assuming that the orbit is circular is not really an inaccurate assumption. So to remain nadir pointing, we can expect that the angular velocity will be equal to about the circular rate of the orbit. Finally, to conclude, class was able to identify many errors in the CubeSat bus design, including high sensor resolutions, a sign flip we had in the control algorithms, and the wrong magnetorquer installation. All of these errors were mission critical and could have caused the mission failure. So class is offering an easily customizable and modular test system that is helping us reduce the risks of having mission failures and improving our verification and validation procedures during CubeSat development. And the current work that is going on in class is that we are looking to add more space environment models, such as more accurate atmospheric density calculations, solar radiation pressure, etc. We want to also add celestial mechanics to be able to test sun sensors and star trackers. And we want to also add the real-time graphics visualization of the mission and the satellite during orbit, and be able to test other subsystems other than the attitude determination and control systems such as electrical power system and CNDH. Thank you very much for listening. I look forward to joining you in the conference virtually.